Welcome to section 6.6 examples, and we're going to work through some basic applications in both derivatives and integrals, and then an evaluation of an expression that involves a trig function and an inverse trig function using the right triangle technique. So let's begin. The first thing we'll do is we're going to compute this derivative. And since I know that I'm going to be doing a derivative that involves an inverse sine, just to remind myself of the formula for this that's going to be relevant, I'm going to write down that I know that d by dx of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. So that's going to be something that we're going to want. What that means more generally, if I think about this in terms of a chain rule, is that d by dx of the inverse sine of some function u is going to be equal to 1 over the square root of 1 minus u squared, but then I have to multiply by the derivative of the u. Okay? So anytime you have a derivative rule, you automatically have a chain rule form that goes with it just by plugging the u in for all the x's and multiplying by a u prime. This is where people tend to go wrong with these. So let's look at the problem that we're curious about. So this piece right here, this 2x plus 1, that's the u that we're dealing with. So d by dx of the inverse sine of 2x plus 1. Well, I know that the u here is 2x plus 1. And so that means I could use this idea with this u. So this is going to be equal to 1 over the square root of 1 minus u squared times the derivative of the u, which is just 1 over the square root of 1 minus 2x minus 1 squared times 2. Now that problem seems very easy. Where do people go wrong? What happens is people tend to blend the two steps of the chain rule together. So it's very common to see things like an answer like this one right here, but instead of a 2x minus 1 being plugged in here, there's a 2 because people take the derivative of the u and then put that into the function. So make sure when you're doing a chain rule that both parts are there. If you have to write down a rule with x and then turn it into a chain rule like this, then do it that way to make sure that you're not blending the pieces together. The next exercise is an integral. And really, we've only got one technique available to us now, which is u substitution. So one of the things that I might notice here, if I want to do this as a u substitution, is there's not really an obvious one. If I tried u is equal to t to the 6th, then du would be 6t to the 5th dx. And I don't see a t to the 5th up here. Instead, what I want to do is I need to practice recognizing what I call the forms of inverse trig functions. You should notice that the denominator here looks an awful lot like the denominator of an inverse tangent, except we have this t to the 6th down here instead of a t squared. So what my strategy is going to be is to try to write this like it was an inverse tangent. So this integral is going to be equal to, well, there's a t squared on top. If I want to write this expression here so that there's something squared, what I'm going to do is I'm going to change that into t to the 3rd squared dt, because now I've got a squared thing here. And now it looks even more like the derivative of an arctangent. Because remember, d by dx of the arctangent of x is equal to 1 over 1 plus x squared. So whatever this is, it gets squared when it gets stuck down there. Now can I use u substitution? Well, why don't we let u be equal to t to the 3rd? Then du is 3t squared dt, which means 1/3 du is equal to t squared dt, and there is a t squared dt. So with this substitution, what the problem turns into is the integral of 1/3 of a du divided by 1 plus u squared, and that is an arctangent. Finally, we'll just substitute back. So this is a little trickier than the substitutions we've done so far, but the idea is to try to start recognizing when you see denominators that remind you of these inverse trig functions. So the quantities you're going to want to be looking for down here are things that look like 1 minus something squared, 1 plus something squared, or something squared minus 1. And those are the integrals that are going to turn out to be the derivatives of inverse trig functions. The last exercise that we're going to look at is going to be a computation using the triangle method. So I have a sine applied to an inverse trig function. And I need to remember thematically that inverse trig functions produce angles. So this is really like asking what the sine of theta is when theta is the angle that the inverse tangent of x spits out. Well, I could write a triangle down that goes with this, because if theta is equal to the inverse tangent of x, then that means then x is equal to the tangent of theta. And that's easy to write a triangle down for. X over 1 is equal to the tangent of theta. I know that this has to be opposite over adjacent, and so I can write down a right triangle theta x 1. Using the Pythagorean theorem, since a squared plus b squared must be equal c squared, I could write down that this is going to be x squared plus 1. Now, what is the question asking for? Given the angle theta, what is the sine? Well, sine of theta is equal to the opposite side over the hypotenuse of the associated triangle, and that means that I'm looking at x over the square root of x squared plus 1. And so this triangle method, again, it looks tricky, but it really is nothing more than high school trigonometry. If you haven't seen this SOHCAHTOA translation of angles into associated right triangles with trig functions, make sure you let me know so we can work through some additional exercises, or I can point you to some resources about the basic trig functions. The next lesson we'll talk about will be posted next week. 3 is it for this week. There'll be a quiz on Friday like normal, and I will see you guys later.